Thank you for joining our talk. I'm Yuki, software engineer for CyberAgent, and my co-speaker, Gabe, software engineer working for Google. Okay, today we are going to talk about resource fairness and utilization for heterogeneous batch ML platforms with Kueue. So before we talk about main topic, let me quickly introduce Kueue. Kueue is AI workload level scheduler. It is not a custom Kube scheduler. It is a second level scheduler in front of Kube scheduler. Kueue provides a lot of scheduling functionalities for AI training and inference workloads, such as all or nothing semantics, delayed pod creation, and multi-cluster dispatching. Additionally, Kueue is a resource quota manager, which supports quota management across namespaces and clusters, and controls machine flavor preferences like spot and reserved instances. And for sure, fair resource sharing is supported. In this talk, we are focusing on this fair resource sharing. As you know, accelerator devices are expensive resources, and AI workloads consume a lot of accelerators. So we help to maximize accelerator utilizations. Ideally, resource usage should be close to 100%. Additionally, the accelerator amount is limited. So we want to distribute that effectively and dynamically across organization based on project or team priority. In this situation, Kueue provides three fair resource distribution approaches. First is fair sharing with preemption, which can help to maximize the current cluster usage. Second is hierarchical for fair sharing, which can help determine fair resource distribution across organization. Third is admission fair sharing, which can help to make fair scheduling decisions with historical data, so that new workloads can access enough compute. In the next slide, Gabe will describe fair sharing with preemptions and hierarchical fair sharing.
Let's demonstrate Kueue's preemption-based fair sharing. Consider the following structure. We have three cluster queues, CQ1, CQ2, and CQ3. Each cluster queue owns 16 GPUs. We consider cluster Q1 slightly more important than the others, giving it a weight of 1.5. These cluster queues are grouped together into a cohort and can share resources with each other. Finally, note the dominant resource share, DRS, in each of the cluster queues. Kueue uses these DRS values in its fair sharing algorithms to make scheduling and preemption decisions. We're ready to schedule some workloads. We enqueue workloads to each of the cluster queues. Kueue schedules these workloads immediately, and we're using all available GPUs. We enqueue more workloads to cluster Q1 and cluster Q2. Since we lack available resources, these workloads remain queued. Suppose that cluster Q3's workloads complete, which we indicate by painting them green. Now the queued workloads can borrow resources, and Kueue schedules them. We paint the borrowing cluster queues to indicate non-zero DRS values. Note that cluster Q1 has a lower DRS value, given its higher weight. A new workload is enqueued to cluster Q3, requesting 16 GPUs, and there are not enough free resources to run it. This workload should be able to run, however, as its cluster queue owns 16 GPUs. We now see our first example of fair sharing, which kicks in to reclaim cluster Q3's GPUs by preempting workloads in other cluster queues. Stating one of Kueue's fair sharing algorithms, we preempt first from queues with higher DRS values. Which cluster queue will we choose first for preemptions? Cluster Q1 or 2? Kueue's algorithm chooses cluster Q2 and has a higher DRS than cluster Q1. After this preemption, we still lack 8 GPUs and start another round of preemptions. Repeating this algorithm, we select cluster Q1. Now there are enough resources to schedule cluster Q3's workload. Let's schedule it. Not so fast. Kueue's scheduling algorithm is stateless. It doesn't know that preemptions just occurred, and it must choose which of the 3 pending workloads to prioritize in the next scheduling cycle. This is where the second algorithm comes in. We schedule workloads from cluster queues with lower DRS values first. We run a simulation to see the DRS value of each cluster queue if we were to schedule its pending workload. Comparing the cluster queue's DRS values, we choose to schedule cluster queue's 3's workload, as cluster Q3 has the lowest simulated DRS value, and it schedules. Next, we will demonstrate fair sharing with hierarchical cohorts. In our new structure, we have a root cohort, 3 subcohorts, and 2 cluster queues per subcohort. We start by creating some workloads, requesting 64 GPUs. These schedule right away. Although left B, the red node, is borrowing, it has preferential access to the 32 GPUs defined within cohort B, its parent cohort. We can observe this visually. Cohort B is not painted red, having a DRS value of 0. We create more workloads, which also schedule right away. There is now borrowing at several levels. Pay careful attention to the relative color of the nodes. According to the fair sharing algorithm, nodes with higher DRS values, that is, those with darker shades of red, will be preempted from first. Now, a new workload is queued, demanding 24 GPUs. Since this workload fits within the 32 GPUs cohort C is entitled to, fair sharing is applicable, and we search for preemption targets. For this next part, see if you can predict how Kue's algorithm will behave. The algorithm starts at the root and chooses the child cohort with the highest DRS. Consider for a moment, from which cohort will we preempt first, A or B? Kue's fair sharing algorithm chooses cohort A. We apply this algorithm recursively on cohort A. Now, from which cluster queue will we preempt first, left A or right A? Left A is chosen due to its higher DRS value. After this preemption, more GPUs are needed, and we begin another cycle. Consider again which cohort and then which cluster queue will the algorithm choose. Cohort A is chosen again, and of its cluster queues, left A is chosen due to its lower weight and therefore higher DRS value. We repeat this process to reclaim the final 8 GPUs. This time the algorithm chooses cohort B, and in the recursive step, left B. And finally, right C's workload schedules. That concludes hierarchical fair sharing. Now Yuki will discuss fair sharing based on historical data.
Thank you, Gabe. So in this part, I deep dive into the AFS, admission fair sharing. Regardless of fair sharing usage, Kueue makes admissions only when there is enough capacity. AFS adds additional criteria, historically consumed resources in a given namespace for admission. Let's quickly go through how AFS works. As you can see in the bottom of the diagram, Kueue periodically takes a snapshot to store the current computer usage, which means this snapshot is not live information. Snapshots are used to compute the penalty while scheduling, which means workloads with lower penalties are prioritized during admission. And the penalty is computed at a given moment because the snapshot is not live information, and the penalty is calculated as an exponential moving average so that Kueue reflects the proper cluster usage. And the 50% decay is applied to the latest and the old snapshots per half-life, so that Kueue can properly handle historical data and Kueue can avoid retrieving live cluster information, which improves scheduling performance and reduces Kubernetes control plane load. Finally, Kueue evaluates penalty during admission. The deprioritized workloads are still in the same scheduling cycle, which means we leverage this penalty to order the workloads in each scheduling cycle. Actually, Kueue leverages 2 types of penalties. The other type is entry penalty. The entry penalty is calculated when the workload enters to the cluster from Kueue's point of view. The primary reason for the entry penalty is handle bursty workloads creation requests. In the consumed resource penalty case, Kueue updates the usage snapshot periodically, for example, 5 minutes, 10 minutes, and more. So when a user submits job consecutively, the user penalty is not considered. Hence, we introduce the entry penalty mechanism. The latest penalty is considered every scheduling cycle. Alright, that's all. Try Kueue yourself and please let us know if you have any questions. Additionally, during this KubeCon, the Kueue team has a project pavilion, so please meet us by our kiosk and let's discuss Kueue. This is our contact information. Feel free to send us questions. Thank you.